I'm Hiroki Ohtsuji from Fujitsu Laboratories. Today's presentation topic is low overhead remote persistence for scalable low latency file systems. This is the background and motivation of this poster. Distributed systems need low overhead remote write operations to implement parallel applications efficiently. The bottleneck of remote write operations consists of network bottleneck, software bottleneck, and I/O bottleneck. In the past, I/O bottleneck was dominant because we use hard disk drives and flash memory-based SSDs. They require slow block I/O operations. Now we have fast persistent memory devices. It reduces the I/O bottleneck. So relatively, software bottleneck becomes a dominant part of the system. We have to reduce the software bottleneck to improve the performance of remote write operations. This slide describes the detail of the software overhead. Performance bottleneck of a software stack consists of multiple memory copies operations and multiple software layers. The figure depicts what will happen when a client application writes data to a remote storage device. The data will be copied to buffer memory, then copied to socket buffer. Network interface transfers data to remote node. The similar things will be happen on the remote node, and finally, the data will be written to storage device through VFS layer. As you can see, there are redundant memory copy operations and redundant software layers. This should be eliminated for better performance. This slide explains the reason why we have to shift to a low overhead remote persistent model. The left figure is a conventional block I/O model. A remote application writes data to with write operation with a synchronization option by using system calls. So there is a context switching between kernel space and user space. Software stack became complicated and there are extra data copy operations. The right figure describes the persistent memory model. Remote application directly writes data to persistent memory with write and flash operations. Software stack became simple and the number of memory copy operations will be minimized. We can reduce the latency. We can reduce the overhead by eliminating context switching and reducing memory copy operations. This slide depicts the evaluation condition. We evaluated the latency and throughput of remote write operations with different two models. The first one is a conventional model, as shown as DCPM plus write in the graph in the next slide. We use DCPM as just a block device. The client writes data blocks with a synchronization option. Second one is a persistent memory model. We bind the persistent memory to a specific node and run benchmark program on it. The client writes the data with cache, flash, and fence operations to ensure the durability. We use the same hardware, but only the software stacks are different. This is the evaluation result. The left figure is a latency evaluation, and the right figure is a throughput evaluation. X-axis corresponds to the two models, and Y-axis is the latency and throughput. The new persistency model reduces the latency by 78% and improves the throughput by a factor of 11. The new persistence model can improve both latency and throughput of remote write operations. Here is the conclusion and the future work of this poster. Software bottleneck of remote write operations becomes the dominant part of the system with persistent memory devices. The new persistence model improves both latency and throughput. Future work is implementing a complete set of file I/O operations of parallel file system on top of the new model to demonstrate the real benefit. Thanks to the sponsors. Feel free to send emails to us and we are happy to answer your question. Thank you for watching this video.